total input wattage of a fixture can be less than the sum of the lamp and ballast wattages for several reasons. Firstly, consider ballast losses. Ballasts are essential for operating fluorescent lamps, and they consume a small amount of power themselves. This power loss typically ranges from 5 to 15% of the lamp wattage. Take, for example, a fixture with three 32-watt lamps. The total lamp wattage is 96 watts, calculated as 32 times 3. Now let's assume a 10% ballast loss. In this scenario, the ballast would consume 9.6 watts, which is 96 watts multiplied by 0.10. Consequently, the total input wattage to the fixture would be 86.4 watts, which is the sum of 96 watts and 9.6 watts. This value is very close to the specified value of 86 watts, illustrating how ballast losses contribute to the discrepancy. Secondly, the power factor plays a crucial role. Fluorescent fixtures typically have a power factor less than 1. The power factor measures how efficiently a device utilizes electrical power. A lower power factor signifies that there is some reactive power present in the circuit, which does not contribute to the actual work being done by the device. This reactive power can result in additional losses in the distribution system. The power factor of fluorescent fixtures can vary depending on the ballast type and lamp characteristics, but it generally falls within the range of 0.90 to 0.95. This implies that for a total input power of 86 watts, the actual power consumed by the lamps and ballast may be slightly less due to the reactive power component. Thirdly, manufacturing tolerances contribute to variations. There may be slight variations in the actual wattage of the lamps and ballasts used in the fixture. These variations can lead to a total input wattage that is slightly different from the rated values. These tolerances are inherent in the manufacturing process and can affect the final power consumption of the fixture. To elaborate on ballast losses, it's important to understand that ballasts are not perfectly efficient. They convert electrical energy to the form needed to start and operate the fluorescent lamps, and in doing so, some energy is lost as heat. The efficiency of a ballast is the ratio of the power delivered to the lamps to the power consumed by the ballast itself. High-efficiency ballasts minimize these losses, but some loss is unavoidable. Therefore, the input wattage to the ballast will always be slightly higher than the total wattage delivered to the lamps. Let's consider different types of ballasts. There are two main types of ballasts: magnetic and electronic. Magnetic ballasts are older technology and are generally less efficient than electronic ballasts. They use coils of wire and a core to regulate the current to the lamps. Electronic ballasts, on the other hand, use solid-state circuitry to perform the same function. Electronic ballasts are typically more efficient, lighter, and quieter than magnetic ballasts. They also offer features such as instant starting and dimming capabilities. The choice of ballast type can significantly impact the overall power consumption of the fixture. Using a high-efficiency electronic ballast can help minimize ballast losses and reduce the total input wattage. Power factor is another important concept to understand. It is defined as the ratio of real power to apparent power. Real power is the power that is actually used to do work, while apparent power is the product of the voltage and current in the circuit. In a purely resistive circuit, the voltage and current are in phase and the power factor is equal to 1. However, in circuits with inductive or capacitive loads, the voltage and current are out of phase and the power factor is less than 1. Fluorescent fixtures with magnetic ballasts tend to have lower power factors than those with electronic ballasts. This is because magnetic ballasts introduce more reactive power into the circuit. Low power factor can lead to several problems, including increased energy consumption, higher utility bills, and reduced capacity of the electrical system. Power factor correction can be used to improve the power factor of fluorescent fixtures. This involves adding capacitors to the circuit to counteract the effects of the inductive load. Power factor correction can help reduce energy losses and improve the overall efficiency of the electrical system. To further explain manufacturing tolerances, it's important to recognize that no two lamps or ballasts are exactly the same. There will always be some variation in their electrical characteristics due to the manufacturing process. These variations can affect the actual wattage of the lamps and ballasts. For example, a 32-watt lamp may actually consume slightly more or less than 32 watts. Similarly, a ballast may have a slightly different input wattage than its rated value. These small variations can add up and result in a total input wattage that is different from the sum of the rated values. The manufacturing tolerances are typically specified by the manufacturer. These tolerances are usually expressed as a percentage of the rated value. For example, a lamp may have a wattage tolerance of plus or minus 5%. This means that the actual wattage of the lamp can be anywhere between 30.4 watts and 33.6 watts. The manufacturing tolerances should be taken into account when calculating the total input wattage of the fixture. To summarize, the total input wattage of a fluorescent fixture can be less than the sum of the lamp and ballast wattages due to ballast losses, power factor, and manufacturing tolerances. Ballast losses are the power consumed by the ballast itself, which is typically around 5 to 15% of the lamp wattage. Power factor is a measure of how efficiently a device utilizes electrical power, and fluorescent fixtures typically have a power factor less than 1. Manufacturing tolerances are slight variations in the actual wattage of the lamps and ballasts used in the fixture. It's important to consider all of these factors when evaluating the energy efficiency of a fluorescent fixture. Choosing high-efficiency ballasts, improving power factor, and accounting for manufacturing tolerances can help reduce energy consumption and lower utility bills. In practical applications, understanding these concepts is crucial for electrical engineers, technicians, and building managers. When designing lighting systems, it's important to accurately estimate the total power consumption of the fixtures. This information is needed to properly size the electrical circuits and ensure that the system can handle the load. Ignoring these factors can lead to overloaded circuits, trip breakers, and even fires. Furthermore, energy efficiency is becoming increasingly important in building design and operation. Many building codes and standards now require the use of energy-efficient lighting systems. Understanding the factors that affect the power consumption of fluorescent fixtures is essential for complying with these requirements. In addition to the factors mentioned above, there are other factors that can affect the power consumption of fluorescent fixtures. These include the ambient temperature, the operating voltage, and the age of the lamps and ballasts. The ambient temperature can affect the performance of the lamps and ballasts. Fluorescent lamps are typically designed to operate at a specific temperature range. If the ambient temperature is too high or too low, the lamps may not operate efficiently. The operating voltage can also affect the power consumption of the fixture. If the voltage is too high or too low, the lamps and ballasts may not operate correctly. The age of the lamps and ballasts can also affect the power consumption. As lamps and ballasts age, their efficiency tends to decrease. This means that they will consume more power to produce the same amount of light. To maintain the energy efficiency of a fluorescent lighting system, it's important to replace the lamps and ballasts regularly. The recommended replacement interval depends on the type of lamps and ballasts used, as well as the operating conditions. In addition to replacing lamps and ballasts, it's also important to clean the fixtures regularly. Dust and dirt can accumulate on the lamps and reflectors, reducing the amount of light that is emitted. Cleaning the fixtures can help improve the light output and reduce energy consumption. Another way to improve the energy efficiency of fluorescent lighting systems is to use lighting controls. Lighting controls can be used to automatically dim or turn off the lights when they are not needed. This can save a significant amount of energy, especially in areas that are not occupied all the time. There are many different types of lighting controls available, including occupancy sensors, daylight sensors, and timers. The choice of lighting control system depends on the specific application. Occupancy sensors detect when a space is occupied and automatically turn on the lights. When the space is unoccupied, the lights are automatically turned off. Daylight sensors measure the amount of daylight in a space and automatically dim the lights to maintain a constant light level. Timers can be used to turn the lights on and off at predetermined times. By implementing these energy efficiency measures, it is possible to significantly reduce the power consumption of fluorescent lighting systems. This can lead to lower utility bills, reduced greenhouse gas emissions, and a more sustainable built environment. In conclusion, understanding the factors that affect the power consumption of fluorescent fixtures is essential for electrical professionals and building managers. By considering ballast losses, power factor, manufacturing tolerances, and other factors, it is possible to design and operate energy-efficient lighting systems that save money and protect the environment. Remember that regularly maintaining and upgrading lighting systems with energy-efficient components and controls can further optimize their performance and extend their lifespan. Furthermore, it's important to stay informed about the latest advancements in lighting technology. Newer lighting technologies, such as LED lighting, offer even greater energy savings than fluorescent lighting. As LED lighting becomes more affordable, it is becoming an increasingly attractive alternative to fluorescent lighting. When considering a lighting upgrade, it is important to evaluate the different options and choose the technology that best meets the needs of the application. LED lighting offers several advantages over fluorescent lighting, including higher energy efficiency, longer lifespan, and better light quality. LED lighting also does not contain mercury, which is a hazardous material found in fluorescent lamps. When disposing of fluorescent lamps, it is important to follow proper disposal procedures to prevent mercury contamination. Many jurisdictions have regulations regarding the disposal of fluorescent lamps. By understanding the different lighting technologies and their characteristics, it is possible to make informed decisions about lighting design and operation. This can lead to significant energy savings and a more sustainable built environment. Finally, consider the impact of lighting on human health and well-being. Proper lighting can improve mood, productivity, and overall health. When designing lighting systems, it is important to consider the needs of the occupants and create a comfortable and visually appealing environment. Proper lighting can also enhance safety and security. Well-lit areas are less likely to be the site of accidents or crimes. By considering the impact of lighting on human health and well-being, it is possible to create a more positive and productive environment. In summary, understanding the complexities of fluorescent lighting systems, including ballast losses, power factor, manufacturing tolerances, and the availability of newer technologies such as LED lighting, is crucial for achieving energy efficiency, reducing costs, and creating a sustainable and healthy environment. The principles discussed here are applicable to various lighting applications and can contribute to a more efficient and responsible use of energy resources.